It's the top is not visible. Should move. Oh, that go back. Okay. So I hope you can all hear me. So today a lecture about probabilistic computation, and there is not too much content in the lecture. So I will give some definitions, RP, co-RP. We will see I will define the class BPP with two different definitions, and then prove their equivalent. Then I will show that BPP is in P/polling. So every decision problem that can be solved in probabilistic polynomial time can be solved by polynomial sized circuits. And then I expect there will be some time left. So I will explain that I will prove that generalized geography problem is p-space complete. So the thing that we missed last time. Just a moment, I need to plug in the battery. Yes. Well, they're not equal because B-poly contains undecidable problems. Okay, so I'm back now. Yes, so why is probabilistic computation relevant? Well, there are a few problems, a few algorithms that there is another beeping. So there are a few problems that can be solved better with probabilistic algorithms. And one example is checking whether product of two matrices is equal to a third matrix. So I'm speaking about normal matrix product. So it's easy to solve a deterministic. I mean, it's well known to solve it deterministically in n to the power 2.31 and so on. So that there is complex deterministic algorithm like by Strassen or somebody. I mean, starting with research of Strassen. But there is a probabilistic algorithm that can solve this problem in quadratic time. Another problem is prime testing, checking whether a number is composite. It can be solved deterministically in time n to the power 6 plus a little bit, essentially n to the power 6 time. But there is famous test, easy to implement, called Miller-Rabin test that is working in quadratic time, but it's probabilistic test. So it's a second example. And then there is a third example, which is more convincing, which is polynomial identity testing. So what do you get? You get polynomial coefficients. Yeah. So no, not coefficients. You get a polynomial using multiplications and addition. So you get a polynomial on the form 1 plus x times 1 plus x squared, or this 5 plus x to the power 20, and so on. And a different polynomial, 5 to the power x, 5 plus 2x squared, or whatever. So you get two polynomials using additions and multiplications. You want to and powers, and you want to check whether they're equal. Even if the powers are given in unary. So one might think, okay, let's expand this, let's apply distributivity and expand both sides, and then check whether coefficients are the same. But this expansion can become exponential. And so this problem, so it's easy to solve this in polynomial time using probabilistic algorithm. You just choose a random x in some range and check equality. However, in deterministic algorithm, it's not known how to do it in polynomial time.
So the idea is just like hashing. So we're checking whether it's right, and if it's not equal, then it's showing not equal, and if it's equal, then we have one side wrong.
Yeah.
Okay.
Okay, I'm ashamed, and now I forgot whether it's in one variable or many variables that the problem is open, but I think it's in one variable. But so exponents can be given in unary. This I do remember. Okay, so there is the main open problem. So what happens during research? Researchers first find the probabilistic algorithm and then find a way to de-randomize it. So there is a whole community of researchers with certain books that are specialized in de-randomizing algorithms. But here is one of rare examples where it's not possible. And actually, many researchers believe or have this intuition that probabilistic polynomial time computation is the same as deterministic polynomial time computation. So there is a way to de-randomize every probabilistic computation. But the most famous counterexample is identity testing of polynomials.
And factorization is also pretty good solved by probabilistic machine polynomial time.
Factorization, if this was solvable in polynomial time, then RSA cryptography would be in serious trouble.
That's why I'm asking.
Yeah. So when I say testing for composite, is just giving an answer. Is it composite or not? But producing the factors is much harder. And actually, there is in one of the homework problems, there was a small factor problem. And there I said it's if it's NP complete, it would have amazing consequences. Co-NP would be equal to NP. However, if it's in P, it has other amazing consequences. So it's natural candidate of being NP intermediate. Okay, but this is not the topic of the lecture. So yes, it's neither in P nor NP complete. So many people believe that this small factor problem is none of both. There are just a few problems, and they're rarely relevant in industry, but they do exist. Like graph isomorphism is another such problem. Okay. There is a third one, but of course I forgot at the moment. Yes. So now let us go to a definition of RP. This is languages that can be decided by randomized algorithms with one-sided error. So let us just write down the definition. And so, but by the way, what is a randomized Turing machine? It's the same as non-deterministic Turing machine, but we think a little bit differently about acceptance. So non-deterministic Turing machines has two transition tables. And randomized Turing machines has two transition tables, and in each step, it chooses randomly one of the tables to follow. So this is a first definition. So when I say a randomized Turing machine, it's the same as non-deterministic Turing machine.
But I thought that non-deterministic Turing machine arbitrarily chooses one of the.
Yeah. But what's the definition? Just a Turing machine equipped with two transition tables. So formally, it's the same thing. But when I speak about acceptance, I will always write down probabilities. Just warning, it's the same thing. Okay. So we say that A is in RP if there exists think this is randomized Turing machine. So let's say non-deterministic Turing machine. And a polynomial. So there's the two conditions. First, all elements, if element is in the language, then with high probability, the machine should accept this element. Where again, in the computation tree, at each splitting, a child is chosen randomly. So if X is an A, then probability that let's give it a name, probability that M of X accepts is at least 1/2. And if X not an A, then machine should always reject. Is equal to. Oh, and also the machine should run in polynomial time.
I think I somewhere saw the probability of 1 divided by 3. It is BDP.
Yeah, I will speak about this. It doesn't matter what you put here.
Oh, okay.
And X terminates in time P of length of X. Okay, so this is definition. Okay, so let us have. Okay, so again, what is randomized Turing machine? It's a machine with two transition tables. So again, we have a computation tree. And each tree can have, each leaf represents an answer when we give the machine X. And so in this case, we can compute the probability that the machine accepts. So for this, we just have to assign probabilities to every branch. So these two leaves have probability 1/4, these two 1/8, and these so 1/8, 1/16. And so now we can calculate probability of acceptance. And so this means the probability over choosing transition table. Yes.
I do write pair and something small, pair 2, pair.
So P is polynomial.
Oh, P.
Yeah. And here is probability. So PR is probability.
Oh, okay. PR, okay.
And this probability is over choice of transition tables.
And where do we need that polynomial?
Because machine should run in polynomial time.
Oh, okay, okay.
Otherwise, yeah, X would be yeah, any almost every class would be in BPP, in RP. Okay, so let us consider a few inclusions.
Is there some reason why it's called RP?
Yeah, randomized polynomial time. Yeah, but this is one-sided randomness. And it turns out, so the most natural class is BPP, I will explain later. But most problems, most examples, they only have one-sided error. So BPP is with two-sided error. So all examples are either RP or co-RP, so complements of RP, but okay, we do not really need it, so I will mainly speak about it. Okay, so let us look at RP. What can we say? Can we understand that P is a subset of RP? Well, it's
Yeah,
very easy
yeah.
because every non-deterministic Turing machine can be viewed as a deterministic one. We have just 2 times the same transition table. And then there will be basically only one branch. So, of course, this is. Now, the next question, what can we say about NP? And so, RP, is it true that it's a subset of NP? What do you think?
Well, you know that then we have the same machine which runs in parallel time, but without the mistake. So it is the right answer. So it seems like we can decide every problem from NP, but not with actually not always right. So it should be inside.
I'm not sure if I. So you think it's opposite? You think that NP is a subset of.
No. That as well.
Yeah.
Because NP is more strong. It uses the same machine, the same machine at the same time, but gives the right answer always. Not the probability.
Yeah. So what you want to say is, let's recall what is NP. So if X is in the language, there should exist one accepting leaf. If X is out of the language, all leaves must reject. And what we have now for RP, if X is in the language, then more than half of the leaves should accept. Okay, weighted half. Because like, think about all branch leaves equally long, then half of the leaves should be exist. It means that to be an NP, X is in an NP language, if there exists one witness, but X is in RP language, if there exist many witnesses, you can generate witnesses randomly. So it's a very strong property. Okay, so plus RP is in practice, it's as good as P. And so people say, oh, but if it's in the language, I only know the answer with probability 1/2. But you can increase accuracy. How does it work? To increase accuracy. So know that probability is for each X. When you take probability over choices of transition tables, it should accept with probability 1/2. Now imagine that you repeat a computation k times. So what's the probability? So as you repeat k times, and if in one of these repetitions the machine accepts, you know the answer. You can stop and be sure that X is in the language. However, if you have k times reject, then you can be certain that then you can say let's reject it. So what I'm saying is we can use a smaller constant here, and we will have the same language. For example, we want to have a constant here. Let's consider the definition with 116. Okay. How do I prove that the definition with 116? Sorry, I want to have much higher constant. Let's use a stronger definition. Then you will understand what to do with weaker definition. So in practice, I say, okay, being right, the answer being right with probability 1/2, it's unacceptable. Maybe it's for medical application and someone's life depends on it. Then we're not going to gamble with this. Okay, then let's try to improve the threshold and be right in 15/16 of cases. How can we do it? Well, if we have a machine that achieves the weaker goal, we can transform it to a machine that receives a stronger goal simply by repeating the runs of the machine. So simply by repeating the machine 4 times, we only have failure probability of 1/16.
So it's just like repeating the experiment.
Yes. So we run it 4 times, and if in one of these runs it says accept, we will believe that X is in the language. If only if 4 times it says reject, we will believe it's rejected. And now we will arrive with much higher probability. Because if X is if X is in the language, probability that the first run says reject is at most 1/2. Probability second run rejects is also at most 1/2, and we need to multiply these things.
So we can just obtain probability 1 minus X.
Yeah. So if X is in the language, probability that we have 4 times reject is at most 1/16. So we have error like this. And in fact, we can make this error exponentially small. We can run the machine n times, where n is the input length, and have failure probability 2 to the minus n. And if n is large, then this probability is negligible. So even if someone's life depends on it, then if n is a few hundreds, it's as good as deterministic computation. Like probability of hardware failure is bigger. So that we get the wrong result because of some transistors failed, it is bigger. So in practice, it's as good as probabilistic computation, as deterministic computation. Okay. So, yes, what else do I need to explain about? Okay, so there is famous Miller-Rabin test. So people in theoretical computer science who like number theory, or just anyone who likes number theory, should learn this proof in Sipser book.
Primality test.
Yeah, primality test of Miller-Rabin. So there is a case, so it's based on the little Fermat theorem. A to the power minus 1 is equal to 1 modulo A is right? I forgot. Yeah, I think modulo A. No, modulo P. Either modulo P or modulo A, I forgot. Okay, I should not.
Just a second.
Yeah, it's a nice proof, but now I forgot.
A to the power P minus 1 by modulo.
Yeah, modulo P. Okay.
Yeah, by modulo A, it's
So if
that makes sense.
If P is a prime number, then this is true, and then they call it Fermat witnesses. So if P is composite number, then and A is a random number between 1 and P, then this fails with high probability for most numbers. And so this gives a Fermat test. But okay, there is a little detail. There is this for most numbers. So there are just a few special numbers P for which it doesn't work, but there you can do another test and together you're fine.
Well, it's just should be prime. So it should be prime.
Yeah, that's little theorem. But if this test fails, if this equality fails, then you know that P is composite.
Okay.
Yeah.
So we are
So the problem composites is in RP because of this property. So for most A, this fails, except for a few special composite numbers called Carmichael numbers. And there you have to do a little bit different tests. And these tests together. But this is a question of number theory to prove that there are just exist many such Fermat witnesses. And so here, in every branch, we check one of the P witnesses. Okay, and then there is something more like P should be odd, and okay, for the other test there are directional conditions. Okay, but unfortunately I forgot everything. So let's not speak too much about it. Okay, so I defined RP, co-RP are complements of problems in RP, some inclusions. And then it's a big open question whether P is equal to RP. So there exists a class ZPP. I'm just, don't worry about this, just for information. I'm telling you there is a class ZPP where we have a probabilistic machine that must always answer correctly. But here the requirement is that expected runtime is at most a polynomial. So the machine with small probability can run very long. And this is weaker definition. because if machine runs very long, we could choose answer 0 and then apply Markov inequality to prove that this probability that machine runs, like let's say 5 times the polynomial, is at most 1 factor by one. So CPP to the two criteria, expected runtime on input x is bounded by a polynomial in length of x.
So we're now removing the criteria about
And then if machine halts, the answer must always be right. Then m of x is equal to a of x. Answer whether x belongs to a. So these are the two conditions. So there exists same thing. A is in CPP if there exists a randomized machine with and a polynomial such that these two conditions are satisfied. So this is class ZPP and Z. I'm just a side note. So I will not ask about this. I didn't decide about homework questions, so maybe it will be a homework question. This is an NP. What's this is an P space?
What does the meaning of machine holds m of x equals a of x?
Yeah, if machine halts, it will have an answer, accept or reject, and this answer must be correct.
Okay. So just the probability of for one.
Yeah, so with small probability, it can run very long, but if it holds, it must. So I'm just explaining this because there is a hierarchy. So many of the inclusions.
Sorry, but I missed the point when we've proven that RP is a part of NP.
Okay. So RP, what does it mean? RP means that if you take a random branch, you end up in accepting branch with probability 1/2.
Yeah.
P means that there exists, and so X is accepted by the RP definition. If a random branch is accepting branch with probability 1/2. But in NP, the requirement is that X is in the language if there exists one accepting branch. So that's weaker. RP means many accepting branches. NP means at least one accepting branch. If X is not in the language, in both cases, no accepting branches. Okay, so now we have chain of inequalities of classes. So P is a subset of CPP. So the special class, I mean, if you can compute the answer in a polynomial time, sure, a probabilistic machine can do it. CPP is an RP, RP is an NP, NP is an P space is an X. But as far as people understand, but it's possible. So it's not possible that P equals X. We already know this from diagonalization. But it's possible that ZPP is equal to X. So some people believe this. I mean, there is, and I mean, maybe no people believe this, or no serious people believe this, but it's consistent with everything we know. It cannot be ruled out. ZPP versus X. Okay.
So, but ZPP versus X is also isn't the same. Well,
yeah. If you can prove ZPP differs from X, it will be great paper.
It will be that P is equal in P.
If ZPP equals X, then no exclusion.
If they are equal, then P is equal.
Yeah.
Yeah, so it's not.
No, it's not true. Sorry. ZPP not equal to X. Oh, no.
Yeah, it can be okay. I understood. Yes, it can be wrong after space.
Yeah. So it can be that P is different from CPP, but CPP is, yeah. This cannot be. Okay. And yeah, but again, this is philosophical digression. Let's start. Okay, so this is proven, this is finished. Now let us go to the second topic. What is BPP? Here we have two-sided randomness, two-sided error. So let me modify definition. A language A is BPP if there exists a randomized Turing machine and a polynomial P. So is that for all X, probability that AX equals and X is bigger than 2/3. So both for X inside the language and outside the language, the machine should give the correct answer with high probability. So this is a definition of BPP. And so we have that RP is a subset of BPP. So do you understand why this is true? So know that now probability of error must be at least at most 1/3. And we had 1/2 in the definition of RP, but we explained that we could equivalently have 1/4 there. So if we have the definition with 1/4 just by repeating twice, then we are good with the value of the constant. And so in RP, we have if X is outside the language, it will always reject. So this will be true with probability 1. But if X is inside the language, then we are correct with probability 3/4, and this is also true. So RP is subset of BPP. Yes. Okay, but it is not clear whether BPP is an NP. So this is open question. So there are many people who believe that P is equal to BPP. Or there is some evidence because of the randomization. I already mentioned this. And if this is true, then of course BPP is an NP.
Wait a second. The previous claim that if the word is outside the language, then it rejects with the probability 1, and it's okay. Yeah.
So you're speaking about this?
Yeah. But if the word is in
not in language.
No. If it's not, then it's obviously true because we reject with the probability 1.
Yeah.
Otherwise, it's not. If it's in language, then we are accepting with the probability of 1/2, and it's not greater than.
Yeah, but we can repeat twice, and we are. We can change the constant.
So yeah, it's okay. I understand.
Yeah. Okay. Okay, and so there is interesting observation that P equals NP, then P equals BPP. This is also a very nice theorem. It says that BPP is in polynomial time hierarchy. For those who are reading Aurora Barak book, they nicely explain it. Okay, but so a consequence of this is that P equals NP implies P equals BPP. And that means that it will be very difficult to prove that P is different from BPP. So, because by contrapositive, so P differs from BPP implies P different from NP. Just a small remark. Just contrapositive. If this is false, then this is not false.
I mean,
I, yeah. Okay, it's too difficult to prove.
okay,
I
so
need
it's
to
just
have a lecture, yeah.
I
Yeah.
thought maybe I just
No.
missed something.
Yeah, sorry, it's just side information. I should stick to the material.
No, it's
Yeah.
great. I have something to read, but it's just.
Yeah.
Since I'm conspect of the lecture, I'm sometimes got distracted.
Yeah, so you need BPP, this element of sigma 2p. So this you can find in Sipser book, and what I just said is direct consequence. This is called polynomial hierarchy. So by the way, this is, we already met this class. It's NP to the power NP. So BVP is an NP to the power NP. Oh, it's very nice.
So and the sigma 3p, it will be NP with
Yeah.
oracle P with
Yeah,
oracle.
okay, exactly. And then there is also pi for this.
Yeah.
And then there's
Pi.
co-NP with oracle and P with oracle. You know that in the oracle it doesn't.
So the first will be call and the rest will be just the
Yeah.
language. Okay.
Now, before I need to give a second definition. Second definition of BBP, or that just say it is what happens. It's similar to non-deterministic machines. We have a certificate definition and definition with non-deterministic machines. So a verifier had additional input. And now we can also consider polynomial time Turing machines with a second input, which is a string of bits. And so we can say, so there is a small theorem. A is in BVP. If there exists a deterministic Turing machine M that runs in polynomial time in the first input and for a random second input, so it has probability M times Y, and Y is taken randomly inside bit strings of length P of length of X. There's at least two terms. So this is a summary. And the second condition, M times Y runs time.
So the Y string is part of the input.
Yeah. Just like verifier, polynomial.
What's it?
Yeah. There exists a polynomial P such that when we give it a random Y, so here we select Y uniformly over all bit strings of length P of length of X, and we give it a random Y, we get the same answer. We get the correct answer. Okay, so this is a theorem, and I think it's easy for you to prove.
And the theorem itself is just the second definition, or
Yeah, it's a second definition. So we can use. Note that for log space versions, this equivalence does not hold. But okay, let us first prove the theorem. So somebody can explain me the proof. Just to repeat what we did for non-deterministic Turing machines.
yeah. So
Sorry, I should write if and only if. Okay, I will write if with 2x. If and only if.
well, okay, but what's what's the meaning of the y?
It's just we consider polynomial time Turing machines with two arguments, and y is randomly chosen among the bit strings.
Yeah, but it's clear how the certificate is helping us to check whether we are working the language, but it's not clear how the arbitrary string here can help us to understand something about the word.
Okay, so let's go over it. So you say one direction is easy. Is this the easy direction, or it's the other one? Which do you find easy? Okay, somebody else?
Well, first of all, in this direction, we can just throw away the y, and it will be right, isn't it?
Yeah, y is the description of a leaf,
Yeah.
non-deterministic Turing machine. So left is 0, right is 1, I guess.
Yeah, correct.
The backwards thing is the same, I think. You just make a tree, make a machine.
Okay, and then here, yeah. So we interpret y as a leaf, just as a set of instructions: go left, go right, use first or second transition table, and then in the other direction, we just create. So the other direction, we have this machine M that's deterministic. We create a non-deterministic machine, and the first thing what it does is guess the string y. So it uses the two tables. One will write zeros and one will write ones, and then it guesses. The non-deterministic machine guesses y, keeps it on the tape, and then simulates the deterministic machine. So this is easy theorem, and it means that proof of theorem is finished. Okay. So let me. And now let us. Okay, I should speak a little bit about the inclusions. I already spoke about it, I think. Yeah, I already said that. So how let's try to make Venn diagram of all classes we know. So we have L, we already know. We have NL. That's a P. We have CPP. Then we have RP. Okay, and now it's nice concentric. When we have we have. So I already said that RP is subset of BPP. Did we already say that? Yes, of course, yes. Okay, I'm getting retarded.
So now we prove the equality of two definitions, yes?
Yeah.
And what we want next is prove that BPP is subset of equality.
And here we have a little annoying thing, because BPP might not be inside NP as far as we know. Okay. So many people believe that P is equal to BPP. And in this case, it will be an NP, but we don't know it. And then the same is for co-NPs. But if we draw co-NP, we get something like this.
But still, all that stuff is contained in the X.
Yeah, it's even NP space.
Yeah.
And this is an X, and X is an X, and so on. X. So for some reason, lecture goes very fast. I'm worried I forget to explain something. Okay, but now let's prove next theorem. BPP is in P/poly. So do you remember what speech/poly?
When you want to size the
Yeah. Now I have to think which one is best. Let's delete this definition. Maybe have it. But also it's short form. So let us remember the definition of speech-like form. So A is in speech-like form. If there exists a polynomial P, and a family of circuits, C1, C2, C3, and so on. So if the two conditions are satisfied, the size of circuit is bounded by P of n, and every circuit gives correct answers on inputs of its length. Am I forgetting something? These are circuits. Okay. So, I forget about error reduction. That's why the lecture goes so fast. Okay. Yes, I'm sorry. I need another theorem. So you know that here we have this constant 2/3. We can put anything we want there. We can even put 1, 2 to the minus length of x here. This doesn't change the definition. But now we have two-sided error. So we cannot use the same technique as before, but we can use something very similar. So to get this result, we will okay, so A is in VPP if there exists a machine, or maybe the previous machine. If there exists a machine that's always correct with probability 1 minus 2 to the power length of x. So that's the theorem. That if you use 2/3 or this one, it's the same. Okay, strategy is to run the machine many times, a linear number of times, and take majority vote. And this follows by Chernoff bound. But we can do, we are actually a bit lucky because we can even use something weaker than Chernoff bound. We can do like a simple direct computation to bound the probability that if we run the machine many times, then answer will be wrong with small probability. Okay, let's use it with a weaker coefficient. Let us say I will put 89 to the power length of x. Slightly weaker result, but you will see how you can amplify it. Okay, so what is the plan? We will run machine n times and take majority vote. So algorithm run m on algorithm to decide with such a small error probability. It's 8 divided by 9. Yeah, 8 divided by 9. Run m on length of x different random y. Answer majority vote. That's it. And now let us think what is probability that this machine, that the majority vote is wrong?
So we did the run M on X, different random Y.
Yeah, because this definition is still here, I will move the other definition. So I'm using this definition, and M is the deterministic machine with two inputs.
So you're using the same X, but Y you're choosing the.
Yeah. Okay, I am just using this definition because it's on the board and I put 8/9 here.
Yeah.
But both proves it. So with other definition, we don't need random Y and just say a random machine length of X times. Okay, and now we have to bound the probability that the majority vote is wrong. And we know that each answer is wrong with probability at most 1/3. Each answer is correct with probability 2/3. So, well, let K represent the number of wrong answers. Yes. So then we have to sum for K equal to n/2 to n. So we have independent Bernoulli variables. So majority vote. So the sum of wrong answers is binomial distribution. So to get K wrong answers, we have n choose K ways to get it times K times wrong. So we have 1/3 to the power K times 2/3 to the power n minus K. Okay. So let us forget about this. Let us look at this coefficient. They're all bounded by the worst case where K is equal to n/2. Sorry, what am I writing here? Probability to be wrong. Yeah. Yeah, so the minimal times we are wrong gives us worst case for this fraction. So let us look to some of binomial coefficients from K equal to n/2 till n times 1/3 to the power n/2 times 2/3 to the power n/2. Okay. And so this is equal to 2 to the power n, and this is bounded by 2 to the power n. And here we have 2 lines of to the power n/2. And this we can simplify further, so we can bring it inside. We have 8/9 n to the power 2. Oh, my bound was not correct. I know what to do. Okay, but if this is not enough and you want 1 minus 2 to the power length of x, then you just don't repeat it x times, but whatever, 10x times or 100x times. And then you will get this bound. Okay, so we can amplify to any exponent we want. And so this is the result. Error amplification. Error reduction. So in this result, I can put 1 minus 2 to the power minus 2 length of x. So here I put a very strong result because I will need it in 1 minute. So it's clear how to prove this, right? I proved it for 8/9 times n/2. But if I use not x, but cx, like 100 times x, I would get a better power. I could get 1/4, yeah, 1/4 in the debate. Okay. So now we are good. prove next result that BPP is in P/poly. It's also a 3D theorem. Right. Okay. So now I have to come up with, for every length, I have to come up with circuits that give correct answers for inputs of the given length. Okay, so let us now have a look at this theorem. I will consider amplified power here. Note that every circuit has to give answers. We are wrong with probability 2 to the power 2 length of x, which is much more than the number of answers the circuit has to give, which is 2 to the power length of x for a given length. Okay, so what will be the plan? So we will build a circuit that simulates n and place in it a random y. Then with high probability, this will work for all inputs of a given length.
So, like roughly speaking, we have less errors than the gates.
Yeah.
Okay.
So a circuit has to be correct for 2 to the power length of x inputs. But it only fails for given input with probability 2 to the power minus 2 length of x. So if we apply union bound, we know that there exists a y that is correct for all the inputs of the given length. So we build C of n, x and y. Circuit that simulates. So when we proved Cook-Levin theorem, we explained we can build circuits that simulate polynomial time computation and their size is polynomial. So that's for this first condition. Simulates m on input x, y. And then second step, fix yn such that circuit such that c x yn equals ax. So for all x in 0, 1. So that's the 2 steps. So of size poly There's our 2 steps. And we already know that we can do step 1 from Cook-Levin theorem. We now have to convince, I now need to convince you that we can do step 2, that such a yn exists. And so this is, we know that probability that Cn, so for fixed y, so why does the yn exist? So let us first fix the string x, then we know that probability over y, that Cxn is not equal to yn, is at most 2 to the power minus 2n. Okay, and now probability over y that there exists x of length n such that Cn xy not equal to ax. This is by union bound at most 2 to the power n, 2 to the power minus 2n. Right? So for a fixed x, we have this probability. Now by union bound, that we fail for some, failing for fixed x at most probability 2 to the power minus n, failing for some x at most with probability 2 to the power n times 2 to the power minus 2n. And so this is clearly smaller than, strictly smaller than 1.
So how did you get from the previous line
From
that?
here to
Yeah.
here, it's union bound.
Okay.
So here for every x, we have an event.
So you just said that the previous line is less or equal than the next line.
Yeah.
Okay.
So here we have an event, and here we have 2 to the power n events, and their union of their probability is strictly smaller than 1. So that means there must exist a y for which none of the events happen.
Alan and Spencer are happy with that proof.
Yeah, yeah, it's probabilistic proof. They have a whole book, Alan and Spencer, about probabilistic method. So yes. So we know that this yn exists, and then we fix it in the circuit. Know that in P/poly, we just have to produce a circuit. So we don't need to compute the circuit because it would take exponential time to compute such a circuit, but we don't need to do it. Just we need to prove that they exist, and we get it by just building this circuit and fixing the second input to be yn. And that's it. The theorem is proven. So if there are questions, error reduction we did. And if there are no questions, then we did this. And there is 15 minutes left. So I can do this topic we missed 2 lectures ago about the generalized geography game. So it's a good refresher. So in the exercises, you probably skipped in the seminar. So let me delete everything. So generalized, so geography game, it's a game that's played among children. Like first child needs to say a city, for example, Brussels. And then the second child needs to say another city, Singapore. That's and the first letter of the new city has to be the same last letter of the previous city. So Brussels will become Singapore. And then we have E. City with E is. Okay, I already lose because the child who cannot name a city already lose. But Edinburgh in the UK, or and this also ends with E. No, or G or H, yeah, and H Helsinki, then with an I. Okay, definitely. Yeah, I was not good at this game. So now generalized geography is more general version of this, and so the input is not a list of cities, but just a directed graph. So let us draw some random example. So the input is a directed graph and a start node. So let us call this the start node. And then the players can choose some, and it's allowed to have cycles. Something like this. Okay. And so the players have each in turn, they have to choose The first player will choose an outgoing edge on the current node. And then, for example, the first player chooses this node. Let's use squares for second player and 0. So the first player chooses this node, then second player can, for example, choose this node. And then third player can choose this or this node, and he wins. So the first player who cannot choose a neighbor loses. So the loser is the one who cannot find a neighbor. And so how does it connect to the game I described with the cities? So there are two cities and they're connected by an edge if the last letter of this city is equal to the first letter of this city.
So, but if we want to study the asymptotic, we need to say that we have infinite mass for many cities here.
Yeah. So the general game is just on any graph, and we forget about the cities. So cities is a special case.
Mm-hmm.
And actually, there was exercise that explained it's a bad example because with cities, even if you consider arbitrarily long names, if you are working on finite alphabet, then you can solve it in polynomial time. So actually, with cities, it's not a good example, but it's so famous. So why not study it?
By solving, we understand that if we give a starting node, we should say who will win. Yeah.
Yeah. So the question is, does the first player have a winning strategy?
Mm-hmm.
Yeah, good point. Yeah, I forgot to explain this. So let us look in this game. This is just an example. Let's remove the game. And let us ask, which player, does the first player have a winning strategy? What do you think?
Yes.
So again, a node can only be visited once, and the winner is
we don't have the direction on all edges.
Yeah. All edges are directed.
So yes, he has the winning strategy. He should pick those edges which were green.
Yeah.
And after that,
yeah. So he can go in this move. He can go here or here. But in both cases, yeah, he wins. So first player has winning strategy. Okay. And so now we want to prove that this game is p-space complete.
So, but basically it's just a TQBF. So we have quantifiers that we want that for any choice of our opponent, we have opportunity to. There is existing a move of us in one moment of the game that we again pick that opportunity, and for any answer of our opponent, and so on.
So okay, let me write it a bit. Input directly. Graph G node S representing the start node. Question has first player winning strategy. Okay, so now let's recall TQBF. So we get a formula in Boolean formula with quantifiers for all variables. So we get like Q1, X1, UN, Xn, and then phi of X1 till Xn. And the question is the formula too. Is the quantified. Okay. And so for every quantified Boolean formula, we need to come up with a graph so that if formula is true, then the first player has a winning strategy.
Mm-hmm.
And if formula is false, then first player doesn't have winning strategy. So now I will write down this graph. So let me use an example. So for example, X for all Y, there exists Z, and then I have X or Y and Y or Z and not Y or not Z for it. Square brackets to be consistent. Okay, and then this formula will be mapped to a graph, and there will be closed gadgets and variable gadgets, like in many reductions. And variable. So know that I can assume that variables have alternating quantifier because I can always insert extra quantifiers, dummy variables. So the start node will be here. And then let us also assume that the first player is exist player. So note that Boolean quantifier formula, we can view it as a game already with two players. Exist player who wants to make the formula true, and for all player who wants to make it false. The formula is true if and only if exist player has a winning strategy. So how does it work? Exist player chooses exist, so they go over all variables from left to right. Exist player chooses the existential variables. The other player, the universally quantified formula, and exist player wins if this formula is true. If for this assignment we get true, he loses if assignment makes it false. Okay, and so now we can understand the reduction, like we will have a splitting here that corresponds to x being true, or x equal 1, or x equals 0. And then we come together. This is just some garbage. And then we will have y equals 0 and y equals another splitting, like this. And in this way, when both players go through the gadgets in this way, so then we have something similar.
So for all variables, you are adding two edges, whether they equals 1 or 0.
Yeah. Okay. And then in the other edges, players have no choice. And then when they come here, we will. But by the way, I'm using TQBF, where phi is in CNF now, and it was exercise to prove that's equivalent. Okay, and then we go here. Maybe I need to insert a node. I will see it soon. But now, for every clause, I will make an extra node. And the plan is that, so here is exist player, here goes for all player. So I'm just marking the edges so that I got the construction right. And let's do it then. So there is an exist player for all, exist for all, exist for all. So I need another one. And then when we are on this node, we will choose the close gadget. And so here we have X or Y, Y or Z, not Y or not Z. And so these are connected to opposite literals. So let's use a red color because it's kind of critical edge. So X goes to opposite literal. X or no. What am I doing? Left. X or Y. Y or Z. Here we have not Y, not Z. Okay, so that's the reduction. And all these edges go to the left.
Wait a second. How do you connect the clauses with?
Yeah, so here is X or Y, and we connect to the literals that make them false.
So strictly false.
Yeah.
And if we have a negation, we connect to the
Oh, sorry. No, I did the opposite. Sorry. I mean, I need to connect them to. So if they're.
So now you have negations to the true.
No, it was correct. Yeah, I did it right. Yeah. Okay. So the plan is that if all the literals are false, it means that all these nodes were already used. For example, if X equals 0 and Y equals 0 was chosen already, it means that the game had passed here. And it means that this clause is false. So note that here we have a for all edges. And here we have exist edges.
So we want all clauses which corresponds to the picked edges are named.
Yeah. Okay. So now finally I wrote down the reduction for this example. So let us say what is happening. Let us say okay. So construction, its clear number of edges is proportional to number of literals that appear plus number of variables. So number of edges is polynomial in the size of the input. That's clear. Now we have to check that this is equivalent. That this is true if and only if this is true. So let us assume that this is true. It means exist player has a winning strategy. What will be the strategy in generalized geography game? So exist player will choose the value of X according to his strategy. Imagine he chooses 1 here for X, which is normal because X only appears positively. So he will go here. So he will go here. Then there is for all player has no choice. Exist player has no choice. Now for all player can choose anything he wants. For example, he can choose 0. There is no choice. And then exist player will play according to the strategy and formula game. For example, choose Z equal 1. I hope it's right. And then he goes like here. Then they alternate a few times. And here the for all player can now choose the edge. And if formula is false, he will choose the clause that is false. So whatever, maybe this formula, if he thinks this one is false, he might go here. Now, if this clause is false, it means all of its literals are false. If all of its literals are false, it means that the game has already passed there. For example, Y is a false literal because Y is 0, but Z is a true literal. So imagine that we went here, then this node was also used, and it means exist player has all his moves blocked, and exist player loses. But in this case, he has a move because Z equal to 0 was chosen, and the last he can go here. And now, oh, okay, now there is a problem. No, there is no problem because this node is already used. So when exist player goes here, he has no moves left because this node is already visited. It's clear? So yeah, okay, let me say again. So what's happening? Players alternate and choose their variables.
Yeah, the left
Then
side
they
is
come here.
more or less clear.
Then close that is false means that all literals are false.
Because you wanted to
Yeah, yeah.
X and Y both be negative,
sorry.
and
Yeah,
if
yeah.
they are negative, they already use.
My fault. Yeah.
No, why is that? It was right.
Yeah. Sorry. Yeah. It's right. Yeah. Okay.
Because am I correct that if they are negative, then we already picked them.
Yeah.
So they will be. It will be negative X or Y will be negative only if both of them are negative, and if they are negative, then
Yeah. So if exists player chose here,
Mhm.
then this option was no longer available.
Mhm.
But this literal is also no longer available. Yeah, you're right. And if y equals 0 was chosen, so this edge is not available. So this is a better example. If also x equals 0 was chosen, then exists player has no move. So all the false literals, they are blocked. And so if all the literals are false, he cannot go there. So that means if formula is true, then first player has winning strategy. And for the same reason, if formula is false, then for all player has winning strategy. We do the same analysis.
Mhm.
So for all player will choose according to his strategy. And then for all player comes here and he chooses the clause that's false.
Mhm.
Since the clause is false, all the moves of exist player is blocked. Okay, so I guess that's the end of the proof of the reduction. I forgot to explain that generalized geography isn't p-space itself. So I proved p-space hardness, but then this is exercise why it's in p-space itself.
Mhm.
But actually, when you reduce to TQBF, you get it for free. That it's in p-space.
Because the reduction is polynomial space.
Yeah. And we already know TQBF is in p-space. Okay, that finishes the lecture. So I will tell Nikita to start 5 minutes later at 7:45. Okay, see you next time.